Hello, this is Yulin, and I will explain the homework 11, problem 1 and 2. The first problem is the stochastic process X is real WSS without the correlation function R tau, and the power spectrum density function S omega. So we need to show that the autocorrelation function is real and even. It's obvious to show that the autocorrelation function is real because the r-axis of tau equals to the expected value of x of t plus tau times x of t. If it's not real, so this part should be conjugate. So this could tell us that the autocorrelation function is real, and we also need to show that this function is even because we could use the result above that this function like this is the expected value of x of t plus tau times x of t. So we switch the position of these two and use the definition. We know that is the r-axis of minus tau. So that shows the autocorrelation function is even. And the second is we need to show that as the power density function is even and non-negative. The first one is we need to show that it's even. By the definition, we could write the power density function like this, and it's the Fourier transform of the autocorrelation function. So we could use Euler formula to rewrite this complex part as cosine omega tau minus j times sine omega tau and d tau. So we depart this function, and it's two parts. The first one is real part. The second one is imaginary part. So this part, we know that r-axis of tau is even, and sine omega tau is odd. So the product of these two is odd, and an odd function, and we integrate from minus infinity to infinity, so it equals to 0. The second part is 0, and the first part is even. So we could know that it's even. And for a bandpass, and the second, we need to show that it's non-negative. Non-negative means that for a bandpass, we could use an example to explain this. We suppose there's a bandpass system, and the pass band is omega 1 to omega 2. And we know that if we want the output square the expected value of output square is greater than 0, and we also know we could rewrite this like this, and the autocorrelation function, the autocorrelation function Fourier transform, and we know that it's the transfer function. The transfer function is 1 in this interval. So in this interval, we could write the s-axis of omega greater than or equal to 0. And because we don't really set the passband, so this interval could be any interval. So that we prove s-axis of omega is greater than or equal to 0. So that shows the density function is greater than or equal to 0. when process x of t is real and WSS wasn't stationary. So the second problem is there are three kind of functions. So we need to show that whether this function could be a function, a autocorrelation function of a WSS stochastic process, or it could be a spectral density function. So the first function is in this form, and in this form we know that it's greater than or equal to 0, and we find its power density function. So use the formula, we find its power density function is 2 divided by 1 plus omega square, so it's greater than or equal to 0. And so we could know that R of tau is non-negative, and S of omega is non-negative. So it could be a autocorrelation function. And if we write it as a power density function, so we know that it's greater than 0. It's greater than or equal to 0. So this function could also be a power spectrum function. And the second one is the sinc function square. Sinc function square. We know that sinc function square is some triangle signal. Triangle signal, and this function also greater than or equal to 0, and the R of tau is also greater than or equal to 0. So this two, we know that is satisfy the condition of this function could be a autocorrelation function, and S of omega is also greater than 0. So it also could be a power density function. The third one is some in this form, and the R of tau. We know that the function of the this function's Fourier transform could be written as some sinc function. This sinc function is not always greater than or equal to 0, so it's not non-zero. It's not non-negative, so it can be a autocorrelation function, but it could be a power spectrum because this function is non-negative. Thank you. That's it.